Conservation of momentum. By the end of this lesson, you'll be able to describe whether an interaction between two or more objects is elastic, inelastic, perfectly inelastic, or if it's an explosion. Some vocabulary to accomplish that. Of course, we have our conservation of momentum, which tells us all of the momentum in the beginning has to equal all of the momentum in the end. Collision, two or more objects crashing into each other and resulting in either two objects or one object if they stick together. An explosion is one object instantaneously becoming multiple objects, does not need to be violent, and energy appears to increase. Spoiler alert, it doesn't. An open system, remember that if an object or collection of objects that we care about, the system, that experiences an external force, which means that energy or matter, mass, can go into or come out of the system. While a closed system, everything is conserved within that system. Elastic collision is a collision where momentum and energy are conserved. An inelastic collision is a collision where momentum is conserved and energy is not. Impulse is the change in momentum brought about by an external force acting for some amount of time. An isolated system is a system that does not have an external force acting for some amount of time. This would be two carts crashing into each other. Our system would be composed of the two carts. There is no external force, but there still is something happening with the speeds. So we would call this an isolated system if there is no impulse acting on the system. Whenever we have conservation of momentum, same problem-solving strategy that we had before. Identify a collision or explosion that's taken place. Draw your coordinate system so you remember positive is wherever you want it to be and negative is wherever you want it to be. Write your equation, all of the momentum in the beginning. Substitute your variables and substitute your quantities, being very careful to be legible with your writing and very careful with your subscripts because these equations can get a little bit hairy. When do we use it? We use it when two or more objects crash or collide in an isolated system. We use it when one object becomes multiple objects from some interaction, the explosion. A cart of mass 10 kilograms is moving 10 meters per second to the right. A second cart of identical mass moves 5 meters per second to the left. Two cars stick together. Keyword there, stick together. That means our two separate masses are becoming one. We can use conservation of momentum to predict the velocity of the two cars after the collision. I don't know if that's what I do. Let's find out. There they go. All right. To solve this problem, conservation of momentum, we start off with two objects, so we have two momenta. And in the end, we have the combined mass. So we'll go ahead and substitute that in. We find out the combined mass at the very end is 2.5 meters per second after we plug in the numbers. Not too bad. The biggest thing here is identifying it's a collision and identifying the system is isolated from other forces, so we don't have to worry about impulse. For an elastic collision, cart M1 of mass 10 kilograms is moving to the right at 10 meters per second. A second identical cart, M2, is moving 5 meters per second to the left. The two cars collide, then move in opposite directions. Derive an expression for the final velocity of M2. Pause the video, try it for yourself. Here we go. So they crash, and now they're going in opposite directions. Start with conservation momentum because they collide. We have two momenta in the beginning and two momenta in the end. Now we expand those equations, keeping our initials on one side and our finals on the other. And then we're going to solve for whatever it is that we're looking for. We can factor out the m's because they're identical masses, and then solve for the final velocity for cart 2. For the inelastic collision, two carts, A and B, are on a frictionless track. Cart A with mass 2 kilograms is initially at rest. Cart B has a mass of 3 kilograms and is moving towards cart A with a velocity of 4 meters per second. After the collision, cart B is observed to move in the same direction with a velocity of 1 meter per second. Determine whether this collision is elastic or inelastic. To figure out if a collision is elastic or inelastic, we have to figure out the total kinetic energy in the beginning, and it needs to be compared with the total kinetic energy in the end. If they match up, if they're exactly the same, then we're dealing with an elastic collision or perfectly elastic collision. If they do not match up, if there is any decrease in kinetic energy after the collision, then we're dealing with an inelastic collision. If there appears to be extra energy afterwards, then we're dealing with an explosion. So, first we need to calculate that initial kinetic energy of cart A plus kinetic energy of cart B. Using 1/2 mv squared, we get 24 joules. Next, we're going to calculate the final kinetic energy. 1/2 mv squared plus 1/2 mv squared in the end equals our final kinetic energy. 1/2 2 times... Oh, we don't have the final velocity for cart A. So now we're going to move to conservation of momentum to figure out that final velocity for cart A. So, using our conservation of momentum, 2 carts in the beginning, 2 momenta in the beginning, 2 momenta in the end. Substituting in, putting in our numbers, we get the final velocity for cart A is 1.5 meters per second. We'll plug that in over in the kinetic energy calculations to see if they are equal to each other. They're not. It appears like we lose a significant amount of energy, of kinetic energy, which indicates this is an inelastic collision. Here we have an explosion. 2 carts A and B are next to each other on a frictionless track while at rest. Cart A has a mass of 10 kilograms and cart B has a mass of 3 kilograms. A fully compressed spring is between the 2 carts. After some amount of time, the spring is released. Cart A is observed moving to the left with a speed of 5 meters per second, while cart B, we don't know the velocity. So let's figure it out. We're going to start with conservation of momentum. In the beginning, the 2 masses are together and they're not moving, so our initial momentum is 0. Our final momentum is mass A times VAF plus mass B times VBF. Remember, we're solving for VBF. Plugging in our numbers, we get 5 meters per second. This is positive, so this tells us it's 5 meters per second to the right, because we've said that to the right is positive. Now let's check on that kinetic energy so we can see what I was talking about earlier with this apparent increase. We started with 0 joules of kinetic energy in the beginning because the 2 carts were at rest. Then in the end, plugging in our numbers, we see that 0 does not equal to 162.5. More kinetic energy in the end indicates an explosion. The extra energy is converted through an internal force doing work to convert stored energy into kinetic energy. In this case, the energy was stored within the spring. It could be that there's chemical potential energy being stored. If you have 2 people on ice and they push off of each other, that would be stored chemical energy. Next, do lots of practice. There's an AI prompt for some extra questions. Don't forget about 2 dimensions. Whenever you're dealing with conservation of momentum in 2 dimensions, we have to treat x and y independent of each other, so we could have momentum in the x and momentum in the y. And if you need to find the combined momentum, remember to use Pythagorean theorem. Ask each other, ask me for help, keep asking until you get it.